My name is Brad Bradshaw. I'm president of the Hydrogen Energy Center, and this is the inaugural Hydrogen Friday series. And we would like to hold more of these Friday events, so we appreciate your involvement here. I'll show the schedule of these Friday sessions in a little bit. Today, what we'll do is use the chat box for question and answer when we get to that phase. And I've asked Doug Brown to assist in looking at the questions and letting me know what they are. We can probably do that, Doug, verbally, and I'd also like Rick Smith to help out in that regard too. With so many people on the call, I don't think that raising hands is something we'll be able to do per se. So I appreciate your forbearance in using the chat box in this regard. The material that's prepared for today is focused on decarbonizing the gas grid with hydrogen, and we've got a fair number of slides, and so I'll zoom through those. Thank you, everyone, for providing questions about what you're interested in topic interest in advance. That was very supportive. It's great to be able to use that kind of dynamic in this modern age. So hold on a sec. Still haven't got the lighting in super good condition here, but we'll do our best. So Rick or Doug or Steve or Dick Meyer from the Hydrogen Energy Center, is there anything else that we need to announce at the beginning?
I don't think so, Brad. This looks pretty good. I thought the information that was supplied immediately after people registered was terrific. And of course, we do have the list of the next, I think 9 sessions altogether, I think I saw listed.
Excellent. So we have a presentation here, and can everyone see that fine?
Yes, at least okay. I can.
So today's agenda is to provide a little background on some of the organizations that are making today's session possible: the Hydrogen Energy Center, Valerity, and then also to introduce a concept of the Renewable Gas Consortium. I've been asked by a number of gas companies to help them fill some gaps in their needs in the region, and we'll just present that quickly. And we'll talk about what the pressures are in the natural gas industry. And it's amazing how quickly these pressures have come about. It's somewhat surprised everybody. 2 years ago, it wasn't considered, but now natural gas being the bridge to the renewable future, it appears that we've crossed that bridge rather quickly. And then we'll talk about hydrogen. Is hydrogen, the ultimate solution, or is it a chimera shimmering in the desert? And we'll talk about hydrogen pathways. And there are multiple hydrogen pathways to integrate with decarbonizing the gas grid. The Hydrogen Energy Center is a professional association that's been focused for, I think, 25 years at least on accelerating the renewable energy economy with hydrogen as a key solution. And the Hydrogen Energy Center provides public forums, conducts research, implements projects on using hydrogen as a key element for the clean energy future. And we certainly would like to encourage all of you to become members of HEC and to be part of the network of professionals and information that we share, and events that we put on for members, etc. So all that information is available at the hydrogenenergycenter.org. And we appreciate, we've got new members that have come on in the last week, and we appreciate your support. The upcoming hydrogen sessions are scheduled out from now into June. And you can see that the follow-on sessions, the long duration storage with hydrogen is next week. Long haul trucking is the following week, etc. So you'll receive messages about these upcoming events, and we certainly encourage your participation. Power production with hydrogen is May 21st. I know I've received a few questions on that, and we do have that topic coming up specifically. The company I run is Valerity, and we provide a series of services to gas companies, equipment manufacturers, and project developers in this space of renewable gas. Hydrogen certainly has been a topic. I've been on quite a number of panels helping explain to people what the hydrogen world is like and what the implications are for the energy transition. This is just an example of some of the companies that I've individually worked for in helping them develop new products and services, investigate technologies, look at markets, raise capital, etc. One of the reasons we're talking about renewable gas is in the last 5 years, we've been investigating, both Valerity and the Hydrogen Energy Center, a number of potential projects in this area. And we were hired by the Small Business Administration and the Connecticut Center for Advanced Technology to assess market development opportunities for hydrogen in the Northeast. Oh my goodness. And 2 areas came out of that work for focus. If everybody could put their microphone on mute, that would be appreciated. The 2 areas that emerged, one was island grids. So literally islands that are putting in solar plus storage to eliminate diesel. We found that it was economic to add a hydrogen storage solution for power as well, because most island projects were only putting in about 50% new power and keeping the diesel because it was too expensive to provide the storage through lithium-ion batteries. And hydrogen has a role in helping bridge that final gap. The other more interesting element in the marketplace, however, became the use of hydrogen in renewable natural gas projects. And this is a key finding, which is biomethane from landfills and anaerobic digesters includes a mix of methane and carbon dioxide. It's typically about 55% methane, 45% carbon dioxide. And to produce renewable natural gas, you need to clean out the carbon dioxide. You need to separate it out through membrane separation, and there are other chemical processes that are used as well. Pressure swing absorption, PSA, is the major one. Consequently, when you have these biomethane projects, they're emitting carbon, and hydrogen can be introduced into the process to absorb that carbon and turn it into more renewable natural gas and through methanation. And this process actually increases the yield of methane from these projects by 70%. It's a increase in the amount of methane that these projects produce by 70%. So it's fairly significant. So this is where our studies, we looked at a project in Lincoln, Maine, which was cow manure to renewable natural gas. Rumford, Maine, at the paper mill, we looked at wood waste gasification combined with hydrogen methanation. And we also, we looked at a project in Brunswick, Maine, as well as Niagara Falls, New York. One slide on the Renewable Gas Consortium to advance this area. We expect it to be a $10 billion development in the Northeast in terms of investment to capture these biogenic sources of carbon and put them to work. And the 4 areas are project development, knowledge forum, policy development, and the industry network. If anyone's interested in learning more about this initiative, please feel free to contact me. So now we're going to talk specifically about what's going on in the gas industry. There are really 4 key drivers here. One is the gas industry is under pressure. There have been bans on new gas hookups. There have been reversals on pipeline plans for expansion. And there are calls in legislation to electrify everything and achieve significant decarbonization. And it is kind of a troubling storyline for the gas companies. We also see that the renewable growth is people are concerned about the stability of the electric system with the high penetration of renewables. On the positive side, we see that renewable costs are been declining. Just was an announcement in India in the past week that a solar PPA was announced for close to 1 cent per kWh. And Saudi Arabia announced the same thing this morning, just over 1 cent per kWh PPA for solar. And that's extraordinary. I mean, that enables very low cost hydrogen. That would be about a 50 cent per kilogram hydrogen on a marginal cost basis. We also have another trend, which is curtailment of wind and solar, which is occurring all over the country. Right now, it's California, it's over 1.5 million megawatt hours a year are curtailed of wind and solar. That's enough power for 300,000 homes full time, which is extraordinary. Just a complete waste of electrons. And this is increasing. And then there's some realization in the industry, certainly Europe is ahead of us in the thinking, which is electrify everything is not entirely realistic, that there are certain industrial processes, city centers, and so on, that it becomes very expensive. And then there's also a concern that if we put all of our heating loads on the electric grid, that we will have difficulty during the deep winter in the north. The south, I think this is much less of an issue. They should be able to electrify all of their heating loads without having too much stress on the grid, per se. So this creates a technical need for hydrogen as well as an economic pathway. We'll go quickly. This is the issue for the gas companies. You can see in the Northeast that the CO2 emission reduction targets, New York and Massachusetts have 85% reduction targets, and the remaining states have basically 80% reduction targets, which is significant. In New York, for example, natural gas is responsible, I think, for 34% of all carbon emissions. And so a future without reducing carbon emissions of natural gas doesn't equate with the aggressive plans in New York, for example. There is, however, a vision or that could be used for the gas companies to actively participate in the future of the energy transition. And one company which is extraordinarily far down this pathway is Vermont Gas, for example. They've embraced pretty much all of these initiatives in terms of defining who they are. They want to see the gas industry put forward a renewable portfolio standard for decarbonizing the gas grid and having it be 2% a year decarbonization of the gas grid. And that's wonderful to see. It's fairly surprising. It's kind of aggressive, but it shows that people in the industry can turn around and embrace this decarbonization pathway and implement policies to move down that path. Questions arise, however. In other words, is there, are there sources of renewable natural gas and hydrogen that are cost effective and can meet the scale required for the industry? Is there a regulatory pathway that enables the business model to be successful? Can you imagine if you have a network of gas pipelines and half of your customers go away? How do you support the remaining capital costs that you've invested in that pipeline on the remaining 50% of your customers? Well, you can't. You need some structure that enables that kind of shift. And so there is a reverse network effect on the economics. And these are the kinds of concerns that need to be addressed. So let's shift to hydrogen. We see that there's a need emerging for hydrogen as a solution. And just in the last 12 months, as everybody has seen, there are a lot of industries that are embracing hydrogen. And there's some concern there because we've got to make it work out, not just technically, but economically. But the same kind of drivers that we've been talking about. We do have a future session that will be on transportation and hydrogen, and we're seeing very large consortia of companies that are embracing hydrogen for long haul and heavy trucking, as well as shipping and aviation, which are fundamentally good use cases. And we're also seeing decarbonizing of industrial applications, steel manufacturing, cement manufacturing, ammonia and refining. We currently produce something like 130 million tons a year of hydrogen around the world, and it is a very large emitter of carbon right now. So that is a big task to decarbonize the hydrogen supply chain, regardless of using green hydrogen for any other applications. So we've seen emerge this whole sort of category of power to gas, and it serves to solve several vexing challenges simultaneously. One is to sop up the curtailed and low regime cost electricity and provide a storage solution in the electric utility industry in order to balance the variable renewable energy on the grid. We can see hydrogen reducing carbon intensity as well, etc. In Europe, there are approximately 128, this is as of last year, power to gas projects. There are different types of projects, multiple feedstocks. Some include methanization, some don't. Europe is well ahead. Germany actually is the leader in this area. The commitments on green hydrogen are extraordinary. And why are they extraordinary? Well, we're going to see a market develop. It's going to increase in size by a factor of 40. I mean, I can't imagine being in an industry and saying it's going to increase by a factor of 40, but that's what's going to happen with the electrolyzer market. 4 countries plus the EU have committed to 100 gigawatts in electrolyzers by 2030. We usually talk about electrolyzers in megawatts, so they're already up at the 100 gigawatt level, which is extraordinary. We do see wind to hydrogen emerging, and we are going to have a session that addresses that. And then ammonia production has been very quick. We see some fairly sizable commitments by industry to producing green hydrogen to feed their ammonia plants. This is a chart on the California ISO wind and solar curtailment, and it's increased 50% between 2018 and 2019. And that increase to 2020 increased by that amount as well. So it's a steady climb in the amount of curtailment. We fully expect that roughly 5% of all the power produced in the United States will be curtailed at some point. This is the projection in the Northeast. We expect to have something like 30 gigawatts of offshore wind developed from Delaware to Maine. And that's an extraordinary amount of wind. And we can imagine, for example, in the shoulder months when the grid does not need as much power, that we're going to have significant overproduction of wind and solar capacity, creating an opportunity for hydrogen. One of the questions that comes up is the color of hydrogen. And we focused a lot on green hydrogen, which is fairly straightforward. You take wind and solar power, and you know, even water power, hydropower, and you run an electrolyzer and produce hydrogen. There also are other methods. I mean, one we'll talk about later today certainly is turquoise hydrogen, which is the methane pyrolysis, which is part of this presentation. And we also are going to talk about blue hydrogen as well, which is just the classic carbon capture and storage with steam methane reforming. They're doing this up in Canada to a very large degree. I think they spent $1.5 billion building a carbon capture and storage system in Alberta that is connected to steam methane reforming. So I apologize in advance for this chart because it's very busy. But let me see if we can help sort of focus on what it is and why we're looking at it. First, we can see that there are 2 vertical pipes in the system. One is a hydrogen pipe and the other is a methane pipe. And we can see going from the left side on hydrogen, we can see sources of hydrogen, the conversion technologies that produce the hydrogen. And then we can see the hydrogen feeding into the use column, which is the central vertical part of this chart. We can see power generation, building heat, CHP, industrial process heat, chemical feedstock, and transportation as the uses. On the right side, we see some similarity for methane, but we're seeing hydrogen blending with hydrogen connecting in and then being blended into the gas pipeline. We can also see methanation producing methane with hydrogen and biogenic carbon dioxide. And we also see in the top right box, steam methane reformation with carbon capture, use, and storage as a solution as well. And we're going to talk about that in the power plant application, because that's an important part of the development going forward. So we can see on the left side, there are multiple sources of hydrogen. Renewable energy and water electrolysis is a large part of green hydrogen production. We have less developed, but still in the technology development phase, thermochemical water splitting and photocatalysis. John Guerra from NanOptic is an expert in this area. He might be on the call. We also have chloralkali plants, which are a major producer of hydrogen today throughout the country through sodium chloride electrolysis. And then finally, we have biomass that can be converted into hydrogen as well. And I did speak to some of the categories on the other side in terms of methanation and blending, which are a key part of our discussion today. The potential for renewable natural gas and hydrogen for the gas companies, in this estimate, it comes out for the Northeast, the far right bars, the blue bar being the total gas demand in the Northeast, which is 1.15 billion cubic feet a year. And the estimate is that a combination of renewable natural gas and hydrogen can meet about 61% of that requirement. And this is the natural gas requirement without the power plants included. These are holding them as a separate category as well. And you can see that different states, Massachusetts from the left, New York, those are the major states. And then you can see New Hampshire, Vermont, and Maine, they have a surplus of renewable natural gas opportunity. Just to mention where the renewable natural gas comes from, this includes both anaerobic digester gas as well as thermal gasification. And it also all includes methanization with the capturing of the excess carbon and utilizing hydrogen to get the increase in RNG production. As well as direct hydrogen represented in the green bar as well. So what are the hydrogen pathways? Hydrogen blending, 100% hydrogen, methanation, hydrogen power production, and pyrolysis. In blending, I had a project that
my sticker. Very good. Hopefully it won't take too long to file.
again, the mute on the microphone button would be appreciated. We have a number of blending projects around the world, more than are listed here, certainly. This Keighley, England project was significant because they did 20% hydrogen by volume on a campus setting with 130 buildings. I do want to point out that the couple of things, 20% hydrogen by volume, it's actually on a BTU basis, it's only 7%. In other words, hydrogen is 1/3 as dense as a gas in terms of the amount of BTUs it holds.
Oh, I'm sorry. Hi there. How are you? I've seen too many people these days, right?
So 20% hydrogen by volume, it's only 7% hydrogen by energy. The second thing is that it's much easier to deploy blending further down in the network. You don't have to worry about compression stations and switch boxes and so on as well. Now, another project in Alberta, Canada, it's 5% blending with 5,000 customers. And the hydrogen source in this case is a hydrogen pipeline that is used by the industry up there. And this is where they're doing the carbon capture and sequestration in abandoned oil wells with post-SMR, steam methane reforming carbon capture. Trying to green up the tar sands. The Markham, Ontario, this is an interesting project because they're building a new pipeline for this particular experiment, but they're only doing 2% hydrogen by volume. So it's not exactly clear why they're doing this. 2% is extremely low. I suspect that they'll be increasing the amount of hydrogen in this pipeline, and they'll probably build it to be 100% hydrogen ready as they go forward. E.ON in Germany is doing a pilot with 20% blend to 400 homes. SoCal Gas and San Diego Gas and Electric have announced a project. They're starting with 1% hydrogen by volume. And again, they're working far down in the network. And I think this is the one where they're testing certain network configurations in terms of the materials that are in the network, in the pipeline, as they go forward. ADCO is the Alberta, Canada project. And additional information is that they'll be using something like 52,000 kilograms of hydrogen per year in this project. So it will have a significant effect, even though it's only a 5% blend. Now, I also want to point out that there's a fascinating project that NREL is leading, which is the high blend project. Mike, are you on the call?
Yes, I am.
Oh, sorry. I think he means me, Mike.
Oh, I'm sorry, Jason.
Plenty of mics out here. Yeah. So Brad, thanks for the introduction. So yep, leading high blend effort, DOE effort. That's $15 million effort looking at material compatibility, techno-economic analysis, and life cycle assessment with hydrogen blending. So I put a link in the chat to the press release on that, as well as was able to list the public companies in that. So I think folks talked about what US companies are looking into it. The answer is a lot of utilities, a lot of gas companies looking at hydrogen blending. So thanks for the shout out, Brad.
Yeah, the importance of the NREL project is to investigate the technical requirements and implications, as well as the economic requirements and implications of hydrogen blending. And it's an excellent initiative, important information for the gas companies. Right now, I think the requirement is that hydrogen can only be 0.1% of the gas in the pipeline. So this is very important to move that number up. Thanks for that, Mike. We also are seeing 100% hydrogen in the gas distribution network. The most significant projects, the H100 Fife program, 300 homes in Scotland. We also have a project in the Netherlands, which they've already done, which is 8 electrolyzers providing hydrogen to 25 apartments, and they're using hydrogen boilers to provide the heat for these apartments, and they have a gas-fired boiler for backup. The next phase is in the Netherlands for 550 homes on a network. They're very aggressive on the decarbonization in the Netherlands of the gas infrastructure. H21 is a project that's been on the books for a long time. Their plan is to inject hydrogen at the city gate of Leeds, and that's 264,000 customers, fairly significant project. Not necessarily underway as yet, as I understand it. This is the LEEDS project, and just to be clear, they include a combination of maintaining the gas infrastructure and using steam methane reforming to separate carbon, and then to put that carbon offshore in deep well sequestration. And then also to include, you can see the little windmills there, to include hydrogen generation through electrolysis, and to have a 100% hydrogen pipeline providing homes and businesses. We also are seeing an effort to decarbonize industry, and this does not necessarily include the local gas pipelines, but it does use direct pipelines, because these projects are being designed on a single user perspective. In other words, feeding hydrogen directly to a manufacturing facility. To decarbonize steel manufacture, for example, is one of the projects. And the other, ammonia, we're going to see a continued growth in ammonia production using green hydrogen. The Iberdrola project in Spain is fairly significant because it's including a 100 megawatt solar facility and 6 gigawatts of electrolyzers for green hydrogen to produce ammonia as part of fertilizer manufacturing. I've mentioned methanation a few times, and this is how it works, which is you have biogas, for example, cow manure going into an anaerobic digester, producing 60% methane and 40% CO2. Then you can add a renewable hydrogen stream to the process to capture that additional CO2 to increase the amount of methane that you produce. What's fascinating is that the cleanup step can be partially eliminated of the biogas by using methanation, because a big expense in the cleanup step is to eliminate CO2 from the biogas stream. And methanation actually can serve that function. Some of the projects that are pursuing methanation in the US and around the world, Summit Natural Gas is pursuing a $20 million project in Maine, which will take in manure from 6,000 cows and 8 farms, produce biogas from an anaerobic digester, and then use methanation to capture the CO2, produce additional renewable natural gas for their system.
Oh,
San Diego in San Diego, SoCalGas is using a bioreactor for methanation that NREL has been working on. It's from Europe. Northwest Natural is putting in a electrolyzer plus methanation for renewable natural gas production. And that same set of apartments in the Netherlands actually did a project for 5 years where they did methanation to produce synthetic methane for heating 25 apartments. So it's a way of greening up natural gas. The development of the system in Summit that Summit is pursuing in Maine, this is just a little bit of detail. They actually use a gathering system. Historically, anaerobic digesters were put on individual farms. Here, there's a gathering system for the 7 farms, and then at the gathering point is a much more major facility, and it can be co-located with the natural gas pipeline and an electrolyzer as well. Maine has significant oversupply and curtailment of wind power that is creating an opportunity for low-cost power for hydrogen production. The same with upstate New York. A really fascinating technology to watch that not many people have heard about is called methane pyrolysis. And methane pyrolysis separates hydrogen and carbon from takes CH4 methane and separates hydrogen and carbon using a high temperature process in the absence of oxygen. And there's a plant in Nebraska, Monolith Materials, which has been operating their plant for a couple of years. They primarily produce carbon black. You can see it, the plant is designed for 14,000 metric tons of carbon black a year, but they also produce very high quality hydrogen in this process. Accordingly, they now are planning to produce green ammonia using that hydrogen, and they plan to produce that ammonia in a much larger plant. They may be investing something like $1 billion to do this. So they're actually going to capture their own hydrogen and produce ammonia. So they'll have a plant producing carbon black, which is used in tires and rubber and so on, and producing ammonia. Another major investment is C0 in Santa Barbara. They just received $11.5 million of investment to develop their methane pyrolysis process. Why is this important? The reason this is important is it enables the gas utilities and the power producers to move natural gas to a power plant using the existing infrastructure and then produce what's called, precipitated carbon or molecular carbon or solid carbon. Basically, it's much easier to deal with carbon dust than it is to deal with carbon dioxide, and be able to produce the hydrogen at the power plant and then have the power plant run on hydrogen using a combined cycle gas-fired turbine. So you can see why Mitsubishi is investing millions of dollars in this technology. Other groups around the world, BASF has a group, in the Netherlands, are also pursuing methane pyrolysis. This is a photograph on the left of the plant that Monolith Materials is operating in Nebraska. And this is a depiction of the C0 facility that I don't even know if they have a location picked out yet, but the company is based in Santa Barbara. So that's it for the structured part of the presentation. And I think we can open it up to questions. I have a number of texts here from Doug Brown that are some of the questions. And Rick, I don't know if you see some questions that might be good, or Doug, if you want to speak up as well. Somebody's asking if the slides will be accessible, and yes, they'll be available.
Brad, there were quite a few questions about hydrogen blending, and I know you addressed blending generally, but I think it would be helpful to talk a little bit more about what has to happen to the pipelines in order to have a larger percentage of hydrogen than is possible now, and the fact that some of the natural gas pipelines that are used today can't take any hydrogen.
Yes, and I'm perfectly willing to hold up my hand and say I have limits to my knowledge. I do understand that in Europe there's been a fair amount of pipeline construction in the last 20 years, and they have purposely made those pipes hydrogen ready. And the hydrogen is about 74% the size of methane. In its natural form, it's H2. And so it does have a tendency to want to leak, but it's not as bad. The new plastic pipes that have been deployed over the last 20 years are impervious to hydrogen. as I understand it, NREL is going to dig into this topic a lot more seriously. So a lot of the last mile pipe that is the plastic pipe is fairly robust from a hydrogen perspective. The issue comes, when you have different metals like steel, when you have compressors, when you have um, control systems. Those are the areas that need more investigation to see if there's embrittlement and hydrogen, intensity increases and so on. But there's plenty of research that's been done in this area to date. I recommend that people dig around and take a look at it. But the last mile is kind of the focus if you look out and see what's going on in this area. The long run pipelines in Europe, I think they've just announced putting 13,000 kilometers of hydrogen pipeline in the ground. And they're not going to repurpose natural gas. They're going to build new pipelines for that purpose. So I think the interstate pipeline systems would likely need to be special built for this application as well.
So Brad, can I jump in here? This is Mike Peters with NREL.
Thanks, Mike.
Yep. So this is something that we're looking at, which is material compatibility of pipelines. And I think Brad nailed it with the, looking at components, compressors, and things like that is really essential here. I wouldn't say that that pipelines today in the ground today are not compatible with hydrogen blending. In fact, likely they are up to a certain percent, maybe it's 10, 15, or 20%. And that's something that we're exploring within our research project. Mostly what you have to look at is the bottlenecks downstream. So where is the natural gas being consumed and what is the end use? And that really will dictate how much blends we can put into the pipelines today. I will point out that the other national labs have extensive material compatibility research out there. So there's a Hydrogen Materials Consortium that's run by Sandia National Labs and Pacific Northwest National Labs. And they are the technical leads on the materials compatibility aspect of our project. So Sandia specializing in metals, PNL specializing in polymers, and they are going to be leading the materials effort within HyBlend. And so I encourage everyone to check out the Hydrogen Materials Consortium, or HMAT, to see what they've done so far. They've got a lot of really good content coming out of HMAT.
Thank you, Mike. Rick or Doug, do you see other questions?
Well, there was a question about nuclear, which is just a little bit afield, but it raises the general issue of where is all this green hydrogen going to come from? The questioner suggests that some of it should be coming from nuclear sources, but even though there's been a lot of talk about nuclear power plants using either excess electricity for electrolysis or excess heat for other hydrogen production methods, I'm not aware of any significant scale projects that are actually doing that now.
Yeah, that's a very good point. There are 3 nuclear plants that have installed electrolyzers to produce hydrogen currently, and they want to learn through this process as well. And what's happened with the power industry is that the wind and the solar considered must run power plants, which means if they're producing electrons, they will displace electrons produced by everybody else, including nuclear power plants. The nuclear power plants are trying to learn how to be variable themselves to do matching in terms of the VRE problem. We usually see nuke as base load, but the nukes are coming out and saying, we don't have to be base load. We can vary our production. So these experiments are going on as well. And I think the one that has been left out is the hydropower. The hydropower people are also suffering with capacity utilization. And they have another issue, which is seasonal water flows during times when the power isn't needed because the grid is filled up with wind and solar. They don't need the hydro. When the water goes over the dam, that water is lost. And so they want to figure out a way to capture those lost water molecules in power. So we're also seeing an interest on their side.
If I may step in with some questions that have accumulated in the chat, may I mention that I have made a list of now 7 questions, and I'd like to start at the top. Now, question 1 was the hydrogen blending that Rick just brought in, and I'll take it that we have discussed the blending, at least initially. We can come back to it if there's interest. Question 2 from Lori Aniti is how to use the curtailment given the diverse methods at each location. I could say what all the questions are and then come back to 2, or just take 2 now.
Yeah,
What would you like?
Take 2 now. I'm not sure I fully, Lori, please feel free to email me afterwards and we'll see. But there are a lot of issues around capturing curtailed power. But one development which is helpful, I want to mention, which is there's been the development over the last few years of what are called virtual pipelines. That's where natural gas is trucked by a truck in compressed natural gas tanks on a trailer, and they're transported to a site which isn't connected to a pipeline. In order to do that, they used to use steel tanks, which were very heavy, and so they hit the Department of Transportation load limits very quickly and couldn't store much natural gas. And so they developed special purpose natural gas trucks which store 4 times as much natural gas using carbon fiber and aluminum tanks, which are a lot lighter and can hold higher pressure. And so you can get upwards of 4 times as much natural gas on a truck. The same technology development has occurred in hydrogen, that the hydrogen trucks on a trailer with compressed hydrogen used to only go 100 miles before they weren't economic. So you didn't see a lot of transport of compressed hydrogen. In fact, that means there are actually production facilities. There are hundreds and hundreds of hydrogen production facilities around the country because of that fact. It's hard to transport compressed hydrogen. But now there are carbon fiber aluminum tanks, which are much lighter and you can hold a lot more hydrogen. So now you can transport compressed hydrogen 250 miles, 300 miles cost effectively. And so that means you can actually use a transportation option to put an electrolyzer at a node in the network and then transport the hydrogen by truck where you need to use it. Not optimal, but another option as well. And the other interesting thing is the electrolyzers are getting cheaper from a capital perspective, which means you can actually use them less time. In other words, you can capture the renewable energy that's sporadic and not have to worry about running your electrolyzer at 90% of the time because of the high capital cost. That's just another detail.
Brad, can I make a comment on some of the issues that have come up? I think it's probably worth discussion that the end use of the gas, whether it's methane or hydrogen, and especially if there's some blend coming out of the pipeline, the flame speeds and the flame lengths of hydrogen and methane are different. And there may be necessary changes that have to be made to just use things like a gas stove with hydrogen instead of methane. You may have to have different burners, and those things are issues that have to be worked through. And it's one of the reasons why you don't see gas turbines that can run on 100% hydrogen that are out there on the market right at the moment. You can probably get something that's closer to 70 or 80% hydrogen as possible right now, but the development is still occurring in that way in terms of the end use of hydrogen compared to methane.
Yep. Okay, so I
Brad,
see.
could I add one more thing to the curtailment item?
Yes, that would be great. We're going to be wrapping in about a minute, so
Oh,
we'll see about following up on some of these questions. This has been great, but go ahead, Rick.
I just wanted to mention the initiative in Maine about taking curtailed power and using the grid to move that power to an electrolyzer that is close to a pipeline. The pending legislation in Maine would allow that to happen without having to pay the transmission and distribution charges to the electric utility, at least for purposes of pilot projects to see if this will work.
Yeah, groundbreaking legislation in the state of Maine to reduce the cost of electricity transmission for hydrogen pilot projects to address some of this
Hey.
distance issue. So, well, I think Talman, you asked a question on ammonia as a carrier. We are going to have a session on that specifically. We're going to look at liquid organic hydrogen carriers, ammonia, liquid hydrogen, and compressed hydrogen as bulk transport mechanisms. Japan is a leader in the investment in this area and the pursuit of this. And there are a number of ammonia projects in Australia and Saudi Arabia, which are going to be, converting hydrogen to ammonia and transporting the ammonia and then pulling the hydrogen back out as well. Jared Alford, I see that you've asked about can the electrolyzer supply chain handle the expected growth? They're making every effort to do that. I think the growth that's going to be amazing, I think, is the electric grid demands from hydrogen production and heating and transportation are going to be significant as well. But I think that's a very good question when you look at a market increasing by a factor of 40 on whether that supply chain will survive. And I think that we are going to see the development of systems that use less precious metals as we go forward, purposely with that reason. The lithium-ion battery market has that potential to put a huge demand on certain metals, and so that's part of that discussion already. So I want to thank everybody for jumping on. We are available just follow-up questions, and we'll have future sessions. Any feedback on today's session is appreciated for us to improve how we handle these. And we will make the presentation available on the website. And so I will send a follow-up email to all of you to provide a link once we get it uploaded. So in the respect of your time today, I wish everyone a great weekend, and thank you for participating today.
I'd like to just add quickly that I have the list of all the questions in the chat, and I will send a message similar to the one Brad sends out that lists them all as I've collected them. And the authors of these questions are invited to explain more if my summary has fallen the mark.
Thank you, Doug. Thanks, Rick, for your help today. Thanks, everyone.